Our next speaker is Atri, and he will continue the discussion on the global 21 centimeter signal. Atri, please.
Hi, I first like to thank the organizer for providing me the opportunity to give a talk here. So I will be talking about how one can constrain the mass of warm dark matter using our previously built MCMC based pipeline called CosmoReionMC. And, and I have done this work in collaboration with it. So yeah. Okay. So let's first look at what is the problem with lambda CDM. So as you know, lambda CDM is very successful in explaining large scale structure. However, when it comes to small scale structure, it shows some discrepancies with observation. So for example, it overpredicts the number of satellite and field galaxies, and that does not match with the observation. And then on top of that, it predicts Kaspi halo profile, which is again opposed to the observationally preferred constant density code. And in addition to that, it also predicts massive concentrated galactic subhalos, which are again inconsistent with observation. So to solve this problem, one way could be that that you can introduce baryonic feedback on top of the n-body simulation, and that has some limited success. And also another way to solve this problem is to delay the structure formation by introducing some kind of dark matter which are lighter than that of the cold dark matter. And this is where we introduce the warm dark matter model. And remember, with warm dark matter model, the mass of the WDM particles are of the order of keV. Okay. So before going into what I have done, let me just give you a brief overview of what we are standing currently in terms of the constraint that comes from different kind of observations on the mass of the warm dark matter. Okay. So here are some of them. So for example, Mimsy et al. In 2016 has published a paper where they have used the UV luminosity function of lensed galaxies at z equal to 6 to put to sigma lower limit on mx, and this come out to be 2.4 keV. Again, there are some other papers, for example, which will count the Milky Way satellite galaxies. Then there will be paper which will work on the Lyman alpha forest data, and there are several other papers which also work on in-body simulations of high redshift halo mass functions. And you can see that all these things come out to be around 2, 2.3, then 3.3 keV. Only there is one paper by Nedler et al. 2021 where they have shown that the lower limit on the mass of warm dark matter comes out to be 9.7 keV, which is pretty higher than all the other values. Anyway, so keeping that in mind, what we are trying to do is that we also again want to constrain the mass of warm dark matter model. So people usually use CMB experiments, sometimes reionization related observations, but we are trying to use 21 centimeter signal observations on top of these two, and want to see if we can put more and more observational probes. Can we put a tighter constraint on the mass of the warm dark matter? That's the goal. And one more thing which is sometimes neglected in some of the papers that I have mentioned is that they sometimes vary some parameters in their model, but they don't vary all the parameters in their model. For example, all the cosmological or the model parameters. So there is a possibility that there might be some degeneracies with the mass of the warm dark matter, and then that with all the other cosmological or astrophysical parameters. So these are the main goals of our project. Let's see. So, okay, so this is the pipeline that I have developed in collaboration with Pete and Saurabh. So what we have done is that we come up with this pipeline where we have used, so this is an advanced MCMC based Markov chain Monte Carlo based pipeline. What it basically does is that it tries to put constraint on several free parameters. The parameters could be cosmological, for example, omega m, omega b, or it could be astrophysical, for example, it could be escape fraction of up to stars. And on top of that, if we want to introduce 21 centimeter model, then there are free parameters which are there in the 21 centimeter model calculation. And it uses this Planck 2018 observation data, reionization observation, and 21 centimeter data. It could be mock, it could be edges. It is up to you how you want to put the observational data, or you want to use mock data. And so what this does is that this EMC basically is the MCMC package, which basically wraps the whole code. So what it does is that EMC first will give you a value of free parameters that we want to compute the posterior of, and then this code will calculate all the observable. some observables are related to reionization, for example, the Lyman limit distribution or gamma pi. There would be some observations which is the angular power spectrum of the CMB, and then there would be observations related to 21 centimeter signal. And once you calculate all the observables, one can calculate the chi-square between the observable predicted from the theory and the observation that actually exists. And therefore, you can put constraint on the different parameters. That's the goal of the code. Yeah. So, with when we use only CMB or reionization model, so what are the free parameters in this model? So, there would be these cosmological parameters, the H0, omega b, omega c, as, ns, which you all of know. And then there would be another free parameter which is basically the warm dark matter mass that is given by mx inverse. Remember, we are not varying mx, we are varying mx inverse. This is very easy to handle with. And then on top of that, there would be some free parameters that will come from our reionization model. One is the lambda 0, which is basically related to the mean free path of the photon. And then there would be the escape fraction coming from up to stars. Okay. And of course, there would be two observations used. One is all the angular power spectrum of the CMB, and there would be reionization related observations, for example, Lyman limit data or the gamma pi data, photoionization rate data. And then we will calculate the likelihood like that, which will basically will be minimized using the EMC algorithm. And so there would be Planck likelihood, which is given in their Planck paper, which is their data release. And then you can calculate the likelihood corresponding to the reionization. And when we use all of these observations and vary all these three parameters, the upper limit to sigma lower limit that we get was 2.8 keV. And now, if you remember the values that are there in my probably second slides where I was reviewing the current literature, you would see that this is kind of consistent with what they have predicted. Okay. And now, once you run an MCMC, I think it is our first thing to check if your model prediction matches with the observation. So, for the time being, just forget about this CMB plus quasars plus edges. Just concentrate on these red things. One is CMB plus quasar, which is basically the reionization, and then there would be a best fit, which is like red, and then there would be random sample that came out from our MCMC analysis once the chain converges, once the analysis is done. And you would see that the red cards are always in agreement with the observational data, and it is also very close to the best fit model, which is what you expect from your MCMC result. Okay. Now, we will see what 21 centimeter signal can do on top of that. So, let us first look at this figure. So, in the x-axis it is redshift, and in the y-axis it is the 21 centimeter brightness temperature. Okay. And it is given in millikelvin. Now, if you look at this curve, you will see that the only thing that I vary in these plots are the mass of the warm dark matter or the cold dark matter. So, you see there is a red curve which is for the cold dark matter, and you will see because cold dark matter in structure formation happens early in cold dark matter, you will see that the absorption trap that occurs earlier in the redshift, say around 22 or so. Now, as we keep on decreasing the mass of the warm dark matter, say 5 to 3, and you will see that the absorption trap will go on increasing, or rather decreasing redshift. So, for example, it was earlier probably 21, then it becomes probably 19 or so. So, you see, as we decrease the mass of the warm dark matter model, the absorption trap shifts at later redshift. So, you would expect that if you can get if you use an 21 centimeter signal, it is only to be expected that you can put a limit on the mass of the warm dark matter. So, before going into this, let me just tell you that given that there is this Saras experiment, Saras 3 experiment, and as a result of which now the 21 centimeter signal status is not clear whether it is true or not, because Saras has rejected it at 2 sigma level. So, what we have done is that we have taken some mock 21 centimeter signal without going into all of this. Okay. So, we have taken some mock 21 centimeter signal data, and we kind of take two scenarios. In one case, we have generated the mock 21 centimeter signal from the 7 keV warm dark matter model, and in one case, we have used it from the cold dark matter model. Okay. So, you will see later that 21 centimeter, which is originated from 7 keV, can also be used as benchmark our code. So, this is the idea. So, now we have three likelihood. One is coming from the Planck likelihood, which is already there. Then there is reionization likelihood, which was also already there. And on top of that, we put this likelihood that comes due to the 21 centimeter signal. and the likelihood will be computed in such fashion. This delta TB/TH is a theoretical signal that we have calculated from our code, and this delta TB, which is originated mock, which is basically the mock data, will be used as if it is the observed thing. Okay, so that's the idea. And okay, and before going into our main result, just once we run the MCMC, you would see that this is the 21 centimeter signal. This is the mock 21 centimeter signal we have used for our CDM model, and we have also, of course, put some noise on top of it. And then you see that once we run the MCMC model, these 1000 random samples which has been taken from once the MCMC run converges, you will see that there is a blue patch that you can see, and that says you that the recovered signal that we have got from our MCMC analysis, it matches the mock data. So that's a sanity check number 1. Okay. Another thing that I promised in the beginning of the talk is that we wanted to see if there is any degeneracy with any other parameter with that of the MX inverse, that is the warm dark matter model. I know that it is very hard to read, so just let's concentrate on this part. So this basically tells you how the MX inverse, that is the mass of the warm dark matter model inverse, correlates with all the other parameters, and you can clearly see that there is no strong correlation with any of the other free parameters. So that was the idea. Okay, and so yeah, so this is basically the result. So let's first concentrate on this figure. So what we have done in this figure is that you can see the constraint on MX inverse coming from all the 3 analyses. One is coming from the CMB class quasars, which I have already shown, which gives 2 sigma lower limit to 2.8 keV, and then this black card, this is generated when we use 21 centimeter signal generated from 7 keV model, 7 keV warm dark matter model, and the blue one is probably our main interest, that is coming from the CDM. And there you can see that when we use a 7 keV warm dark matter model, then the MX inverse comes out to be close to what it should be. Basically, it should be around 7 keV, so it is what it is. And then for the CDM, you would see that the MX constraint is greater than 7.7 keV, and that is somewhere close to the Nedler et al., where they put the limit on 9.7 keV, but it is much tighter compared to all the other results that are there. So we can see that although we are not using any observed signal, because probably there is none at present, once we have a signal, if we have a signal, right now of course it is hypothetical or mock, we can see that once you use 21 centimeter signal, it basically put a much tighter constraint on the limit of the mass of the warm dark matter model. Yeah. So to summarize, we first saw that the lambda CDM model shows some discrepancies with observations in the small scale structure, and that can be resolved once you introduce warm dark matter model. But again, please note that you can also solve some of these issues if you include baryonic feedback in your model. However, the baryonic feedback has limited success. So right now we are introducing warm dark matter models here, and then we have used our previously built CosmoReionMC, and then we use it to put constraint on the mass of warm dark matter model. And we see that when we use CMB and reionization observations and hypothetical 21 centimeter signal, then the constraint on the warm dark matter mass comes out to be 7.7 keV, which is a very tight constraint. And we have also shown that because we are varying all the free parameters, which is what the main power of CosmoReionMC is, because it is very fast and it can vary all the free parameters very efficiently. And you would see that there is no evidence of degeneracy between cosmological parameters and the mass of the warm dark matter. So with this, I'd like to thank you.
So have you tried a mixed model where you have CDM plus warm dark matter in the same model?
No.
Right. And regarding your last point, the no evidence for degeneracy, the astrophysical parameters means there are no baryonic feedback. Okay. Is that correct?
By astrophysical parameters, I mean the parameters that are used in our reionization model. Yeah. For example, the escape fraction coming up. So the escape fraction of up to stars and the lambda 0, which is related to the mean free path of the photons. These are the only free parameters. By astrophysical parameters, I meant only those.
Only those. But if you include the baryonic feedback in those astrophysical parameter list, you will get less tight constraints on your
What
mass
do you
of the
mean by that?
baryonic
Because
feedback
I mean, what I meant is
parameters?
in the reionization there is of course baryon, right? I mean,
No,
I
no,
don't.
feedback. By the
Feedback,
galaxy.
no, there is not feedback.
No, if you include the feedback parameters,
Yes.
then the constraints on the worm dark matter will be less.
It is possible.
stringent.
We have not checked. It is possible. And also remember, once you put more model, it is also possible that the MC incident might not convert. So there is this shred that the MC incident might not convert.
Sure. Thanks. Yeah.
So, Atri, about this astrophysical parameter stuff, shouldn't there be a strong degeneracy between the warm dark matter mass and the Lyman alpha and X-ray brightness of your sources?
Okay, so for Lyman alpha and X-ray brightness, we have used these three parameters, and as it appears in our model, there is actually no strong degeneracy between these parameters with that of the MX inverse. That's what we have seen in our code.
Do you understand why? Because that's really strange, no? Are you not surprised?
Given that there are so many free parameters, it is possible that the effect is hidden in some other free parameters, and as a result of which you don't see anything over there.
Kanan.
So when you include warm dark matter, it changes the halo mass function.
That's true, yes. And also when you calculate sigma, that will also change.
Okay. So when you don't include warm dark matter, what kind of halo mass function you use? Set torment.
Set torment. And when I was using warm dark matter, I take the halo mass function from the Lovell et al. Paper, which they have calculated from the rainbow simulation.
And these are these atomic cooling halos. You are not considering molecular cooling halos.
No, I did not consider molecular cooling. Only use atomic cooling.
Okay. Because I don't know whether set torment mass function is how valid it is at a high rate shift, particularly at small halo mass range. I have seen papers where there are several other models of halo mass function, and they differ a lot, particularly at small halo mass range.
Okay, so what we have done while using set torment, we also use the Tinker model that is there, that comes from the in-body simulation. There we have seen that the result does not change. So I do not know what how these will affect.
Okay. Yeah.
Atri, have you tried to infer these constraints from a null measurement? From a null measurement, like Saras-like measurement. There is no cosmological signal, but that will still constrain your warm dark matter.
No, I have not tried. That's a good idea. Yeah, I have not tried.
Yeah, I have one quick question. Sorry if you have already explained this. You are treating this MX inverse. Is it because the way you want to specify the prior from a particle
it is more like because we know that the MX will be in range of a very say 0. MX value will probably vary from 0 to 1. So MX inverse will give you more flexibility to vary your parameters in that range. So MX will only give you probably 0.1, 0.2. But if you go to MX inverse, it will just inverse the value. That means now you have a bigger range to play around. That being infinity.
Yeah. So this basically changes the redshift where the deep appears, right?
That's true.
But does it also change the evolution of the spectrum at a later redshift where it is?
We have not checked the power spectrum. Our code doesn't compute the